All right. So our next speaker is Dennis Bodewits, who's going to be talking about solving the 60-year-old mystery of the ionic emissions from the coma of 29P.
All right, thank you. Welcome, everybody. Glad you're still here. I'm going to talk about one of our comet people's favorite objects. It's a centaur, meaning that it's an object coming originally from the Kuiper belt, but is gradually changing into a comet as we know it. This object is called 29P Swaggman. And let me just start first with the motivation of my work. So my background is really molecular and atomic physics. So you're going to see a lot of spectra. And one of the tricks that we are trying to make work is that there are a lot of molecules that you cannot easily see. You cannot easily see them from the ground because we have a lot of water, for example, in our atmosphere. But if you look at their cations, so that means you take one electron away from them, then they're suddenly visible in visible wavelengths, making them much more accessible because we have a lot of optical telescopes with spectrometers on them. And so for comets, the ones that are most relevant are CO+, and that's the one that causes comet tails to be blue. N2+, which is great because N2 doesn't have a dipole, so you cannot otherwise spectroscopically find it. CO2+, which you can now do, you can do CO2 from Webb, and H2O+. And so these are, I think, also very important. They represent very different volatilities. And these are very important molecules if you want to connect your comets to disk chemistry. There's just one caveat. They are ions, so that means that something reacted with them, something caused them to be ions. And so there's now two things that you need to know. You need to know what formed those ions in the first place, but then also what is it that excited them and then resulted in the emission of light. So here's 29P Swaggman-Wachmann. It's a big object, about 30 kilometers in size. It resides at about 6 AU from the sun. It is famous for being the most active object in the solar system. It has all these outbursts all the time, sometimes as large as 5 magnitudes, but you can, whenever you point a telescope at it, it's essentially doing something. And so it has a persistent coma, but it also has these massive outbursts. From James Webb, I did not put the right reference in there, but we know that it has about 2% CO2, and the activity seems to be driven by carbon monoxide. So for about 60 years, and that's the big mystery here, we know that there are CO+ cations in the inner coma of 29P. And that's actually kind of strange. So in your normal comet, what happens if you have a water molecule, you expose it to sunlight, in about 1 day, the water is either dissociated or a little bit of ionized, and that's photochemistry. But at 6 AU, you're going to have a factor 6 square, 36 less sunlight. And so stuff should go really slow. If you have a molecule that normally lives for a day, now at 6 AU, it lives for a month before you get those ions. And in that time, of course, the molecule will drift away. So there's two caveats. Why is it there? But why is it also in the inner coma? Whereas we expect it takes a while for those cations to form. Yeah, so that again is an illustration that you have to understand first what causes that ionization, but then also what is the excitation of that CO molecule then followed. So here's just a lot of the different atomic physics that you can use to excite a CO+ molecule. So first of all, you can have fluorescence. Fluorescence is the main process where most cometary molecules emit light. You absorb a photon from the sun, you absorb sunlight, and you re-emit it. Charge exchange. So comets are exposed to the solar wind. That's a steady stream of mostly protons and electrons. They can also produce CO+, and they can also produce excited CO+. Photoelectron impact. So we have ions, CO+. Those electrons have to go somewhere. And you can use those electrons again to produce other CO+ ions, so sort of like a runaway process. And then finally, you have another stream of electrons. Those are, again, solar wind electrons. They have lower energies than the photoelectrons. So that's already 4 different processes for just producing and exciting CO+. Now, the good news is these are all different reactions with different energy balances. Or you're going to produce different spectra. Some processes have more energy to excite your vibrational states. So if you have high-resolution spectroscopy of 29P in this case, and you can compare this with your lab data, you can figure out how much each process contributes. And that's exactly what we're trying to do. Now, what you need for that is two models. First, you need a coma reaction model that looks at those reactions. And then second, you need molecular models that can predict that excitation. And this is an example of a model that is made by a research scientist that I work with, Steve Bromley. And the dots here are old data by Anita Cochran, who showed that profile of the CO plus near the inner coma. You see that's within 100,000 to 1,000 kilometers. And Steve has made those different models, and progressively we're getting closer to that the observed profile. And this what he's finding. So the results are kind of surprising. So our first gut was like, well, because this comet is so far away, you always see it under a low phase angle. So maybe it's just because we're staring right down its tail that you can see so much of it. But there's more to it. And secondly, there was a group from Slovakia, Alexandra Ivanova, and she found that the flux emitted by the CO plus correlates with the solar wind. It's a little tricky to do because you need an extrapolation model for the solar wind, because we typically measure it at L1, and this comet is at 6 AU, so that's a huge extrapolation that you have to do. But it did seem to work. And so then my thought was, okay, then it's charge exchange, which I really liked because I wrote my thesis on charge exchange, so I want to see it everywhere. But Steve's modeling now suggests that those electrons, specifically the photoelectrons, are actually a driver of the emission. So it is a very complex environment where you have to take all those aspects into account, which is kind of cool. So how are we going to do that? So first of all, we're making those molecular models. That's what you see in the top here. So you got to figure out the structure of the molecule, which is quantum chemistry. Then you got to take sunlight, excite that model that you just made, and then look at different parameters and see what the spectra would look at different conditions. And you can see that the spectrum really changes as a function of distance to the sun. So you really have to take that into account. Second, we're doing experiments. So to validate those molecular models, but also to look at electron reactions itself, we work with a group in Slovakia. This is a little setup. The photo makes it look big, but it's actually about this large. And what it uses is a filament, just like you would have in an old light bulb, to create electrons. And you can then control the velocity by voltages. And we shoot at that gas and look at it with a spectrometer. And just over and over again, different energies, you can change all the parameters. And that way we can also create spectra for electron impact on CO and see what that would look like. And then finally, which is of course very relevant here, is we do observations to test our models. And so 29P, as I just said, is like the most active object in the solar system. It's always different. And the same thing goes for the solar wind. There's the weather analogy, and the solar wind changes also on timescales of hours to days, especially now during solar maximum. So what that allows us to do is the parameters of this experiment change all the time. The comet changes, the solar wind changes. And so if you just take spectra as a function of time over a significant time span, you can start correlating things and see how it all fits together. And so an example over here is that the three panels, the top one is comet magnitude. So you see that the thing goes out in an outburst at the end, where it suddenly jumps to 2 or 3 magnitudes. The solar wind speed and the density, look at all there's between 400 and 800 kilometers per second, and you see those jumps in fluxes, which represent shocks. And so that's what we're going to use. We started our observations in January of this year. I got more lab time at New Year's Eve, which was great. We took it in stride. The object is kind of nice because it's available either the last hour of the night or the first hour of the night. And so that has been great for scheduling. They can just slot us in, and we just need a little bit of time. And that's what we'll be doing again this January. That's what I have. Here's my summary takeaway for you. So cations, just singly ionized molecules, they can make molecules visible that you otherwise would not have access to from visible wavelengths. 29P is a unique object that allows for these natural experiments. And what we have to do for that is combine observations, models, and experiments. And I would like to thank the support that we've gotten for this project. Thank you.
All right, any questions? Anyone? Well, I've got one. I would love to know if there are any other comets that are even similar to these you can get similar high resolution spectra of.
Yeah, so this object is kind of unique because it's in a nice and stable orbit, so it's very predictable. Other comets that are that bright are going to be less predictable, but there are comets for which also this CO plus has been discovered at these really large distances, 7-8 AU from the sun.
Thanks. All right, any other questions? You've got a question?
Okay, conveniently have a question. So what are the temperatures for these CO plus, like the kinetic temperature or the rotational temperature, and how long do they live on? Just curious.
Yeah, so we know that from James Webb. It's extremely cold, just tens of Kelvin, and also this is a non-LTE process. It's the sunlight that is re-emitting with 5, 10, 20 Kelvin. That's pretty typical. Okay. Do you like that for your discs?
Well, I'll think about it. Thank you.
Cool. There's time for one more quick question. Yeah, we've got one just up there.
Thank you. Really quick question. On your previous slide, you had the solar wind, solar density, and 29P. I assume that the solar wind and density are measured near 1 AU. 29P is at 6 AU. That little lag you had for the outburst, is that consistent with the solar wind speed?
These are just random dates, but you're right. For the propagation, we use the Enlil model. So that's an MHD model that's maintained by, I don't even know actually, but there is some uncertainty in that prediction, and that by now is about 12 hours. It used to be 24 hours. But I hope that it is enough that we can see patterns in the correlation and help us figure out what exactly the solar wind condition was.
All right, let's thank our speaker again.